Hi guys, welcome to all of you. Guys, kindly confirm once that whether am I audible to you or not. Hi, good evening, Satna. Okay. Shillong, am I audible to you? And please share the topic as well that we were discussing in the last class so that we can proceed. Okay. Share your camport, Shillong, and topic as well. Orbital overlap concept. Okay. So is there any question for me, guys? Anything that you want to ask me? Please go ahead. You can ask me if you have got any query or question. If not, then we can proceed with the new concept. I think we were discussing that the particular given overlap would be positive, negative, or the zero overlap. That was the last topic that we have discussed. Any question for me, guys? Oh, this yes for the question, or we may proceed. Okay, I'm giving you a question. You have to tell me whether the given overlap would be positive, negative, or the zero overlap. Okay. Px plus S along x-axis. Okay, that's cool. Tell me whether the given overlap would be positive, negative, or the zero. Okay. Shillong, what do you say? Okay. Hi, good evening, Kohima. Okay, let's check out. This is your Px, positive, negative, and this is S. So if I talk about this one, so guys, this results into positive overlap as well as in the negative overlap. Okay. Why? Because if I overlap in this manner, then obviously this one results into the positive overlap. But if I change this one, if I change this one and I write it as a positive and negative in this manner, then this one will result into what? Negative overlap over there. Okay. So positive and negative both are absolutely right answers. Okay. I was expecting that you will say the positive as well as negative, or not as well as positive or negative overlap. Okay. Got it? Now tell me this one. Px plus Py along z-axis. Hi, good evening, Itanagar. Tell me what kind of overlap this one can have. Okay, Kohima has given the answer. Both. Okay, let's check out. First of all, let's draw the internuclear axis, which is this one, Z axis. Now they are saying the px and the py's, obviously they would be perpendicular to this one. Okay, this is your px and this is your py. Positive, negative, positive, negative, and might be possible that they reverse, and if they reverse, then obviously this one might be positive and negative. Okay, so quite good answer, Shillong. Remember, we can't say it is a both type of overlapping, we'll say either positive or negative. Remember the word either positive or negative. Okay, I haven't got the answer from the Satna Center. Dear, have you got that? Okay, so guys, that's all about the orbital overlap concept. Now let's move on to the next quite important topic, which is hybridization. Hybridization. Okay, so the question is, why do we need hybridization? What is the reason behind that? See, till now we were discussing about the bond formation concepts. Okay, what have we discussed till now? That the outermost orbitals containing the electron overlap with each other, and after the overlapping they form a bond. Okay, but hybridization says that no, it is not like that. They directly overlap with each other and they form a bond. If this is the only possible way, then might be possible in a single compound. In a single compound, we might get different bond strengths. If different type of orbitals are taking part, are participating in that bond formation, then obviously it is possible that in a single molecule we have got different type of bond strength for the every bond. Okay, so that explanation was actually quite difficult to understand over there. Okay, so just to make easy that how actually bonds will be formed, and yes, few of the shapes as well. Okay, few of the shapes as well has been described by the help of hybridization. Okay, so hybridization simply says that, or we can say first of all that hybridization ultimately is used to determine, or we can say is used to explain that overlapping concept. Okay, that actually how orbitals will overlap, and after the overlapping they will result into the bond formation. Okay, how the new bonds will be formed. Okay, so this is much more appropriate method, or we can say much more appropriate concept for the explanation of the bond formation. Okay, so this is the point that why are we using the hybridization. Now the question is what hybridization is. Okay, so guys, hybridization is nothing but it says that the orbitals having the slightly different energies means that it is not necessary that always those orbitals having the similar energy will be overlapping together. Okay, orbitals having slightly different energies can also be overlap over there, and after the overlapping they form or they generate the new orbitals having different shape from the mixing of if I compare from the orbitals which are intermixed together. Okay, that one will have got totally different shape, different we can say different electron clouds over there. Okay, that will be totally different over there. Okay, it simply says that if two atomic orbitals overlap with each other, then two new orbitals which are known as the hybrid orbitals will be formed over there. If four orbitals are overlapping, or we can say the intermixing, not the overlapping. We will leave that word overlapping right now. We will just talk about the intermixing of the atomic orbitals. Okay. So if intermixing of atomic orbitals participate, having the four orbitals, okay, then after intermixing they will generate the four new orbitals over there. Okay, and they will have the different geometry as I compared from the orbitals which have been intermixed initially. Okay, so this is the brief idea regarding the hybridization. Okay, so this is nothing but it is the intermixing of atomic orbitals having slightly different energies. Okay, and after the intermixing they will generate the new orbitals which are known as the hybrid orbitals having the different shape as I compared with those orbitals which are intermixed with each other. Okay, I hope so it is clear up to now. I'll write all these things for you, but first of all tell me that have you got the brief idea regarding the hybridization, that what exactly hybridization means? That just confirm it to me. Okay, so you can start copying that with me. Okay, copy with me. It is introduced by Pauling. To explain equivalent nature of bonds in a molecule. Now, definition. The intermixing of atomic orbitals of slightly different energies and redistribution of energy to form new orbitals of same shape and energy. These new orbitals are known as hybrid orbitals. Hybrid orbitals actually look like this. Bigger lobe and the smaller lobe. Okay, this is how the hybrid orbitals will look like. Okay. Next, hybridization is a mixing of orbitals and not electrons. Therefore, guys, these are very core important points, okay, that you have to remember. Therefore, in hybridization, fully filled half filled and empty orbital may take part. The number of hybrid orbitals formed are equivalent to number of atomic orbitals which have taken in the part of which have taken part in hybridization process. Each hybrid orbital having two lobes and bond is always formed along bigger lobe. Hybrid orbital are differentiated as sp, sp2, sp3, etc. That's it. Enough. Copy. Just copy that and confirm it to me. And after that, if you have got any query or regarding these 4 points, just you can ask me. If not, then we will understand that how hybridization will take place. Okay. Shillong, Itanagar, Kestapula. Guys, have you copied that? Okay. It's okay, you can copy. Shillong, just confirm after copying that. Okay, let's move on. Now guys, please do not copy anything, just look at the screen. I need one person on the system just to answer my questions. Yes, definitely dear, D and F, not F, actually D orbitals will take participate, means the examples which are available to us, okay, from up to now, up to D orbitals, we have got those examples, okay, but yes, F can also participate, okay, F can also participate, but we are restricted up to the sp3 d3 only, okay, no such example of the F orbital participation, okay. Now guys, please do not copy anything, just look at the screen, understand the concept, and I'm going to ask you a few questions while discussing this concept, okay, so please make sure that you will just confirm with others as well, and you will tell me what answer would be for that, okay. Do not copy anything, just understand the meaning, okay. Let's start with the sp hybridization. Let's talk about BeCl2. First of all, tell me what is the central element. In BeCl2, what is the central element? Yes, beryllium. Atomic number is 4. So let's write its configuration 1s2, 2s2. This is the configuration, okay. This is a ground state, guys. I hope so you know the difference between ground state and the excited state. In the excited state, electron goes to the upper next available vacant orbital, okay. So if I talk you about the next available orbital, that one will be definitely 2p, okay. This is your 2s, this is your 2p, okay, ground state. I have filled the electrons, okay, ground state. Guys, first of all, understand the meaning of the excited state. See, remember in the excited state, what you have to do, take the electron which is paired, okay. First of all, check out the only outermost orbital. See, I am discussing only about the outermost orbital. See, take out the electron of the outermost orbital And if any available vacant orbital is there just next to it, then just place that electron to that one. Okay. So actually I'm going to do the same. This is 2s and this is your 2p. Okay. As I can see here, 2s has got the 2 electrons, so just unpair the electrons. So 1 electron here and 1 electron here. This is 2s and this is 2p. And this is your 1s. Because 1s was the inner orbital, that's why you can't touch its electron. You will only use the electrons which are present outside. Okay. And remember, you can maximum make the half filled. Don't do like that. You have you empty the 2s orbital and place all the electrons to the 2p. No, just make paired unpaired. Okay. What you have to do? Those orbitals which having present the paired electrons, make them unpaired. That's it. Okay. Now this is the excited state. Okay. Excited means where we make the paired electrons unpaired by sending them to the next available vacant orbital. Okay. I hope so everyone has got that. Now just tell me how many orbitals are there which are unpaired, which are containing the unpaired electrons. How many orbitals are there which are containing the unpaired electrons? Okay, very good. Those who haven't got my question, you can please ask me. Shillong, Kohima. Yes, absolutely right. Kohima, are you there? Okay, see. So I'll focus only in these two orbitals. Okay. So actually, these will undergo the hybridization process. Okay. They will participate for the hybridization part. Okay. Now, you can check out. If I ask you, how many s orbitals were taking participate over there? Only one. And how many p orbitals were there who were participating in the bond formation? In the hybridized orbital formation. How many orbitals of the p? Look at this. Check out the box. The red box. Yes, absolutely right. Shillong, Kohima, Itanagar. My question is, how many p orbitals are under the red box? Guys, are you getting my question? Okay. See guys, if you are not getting my question, please you can let me know. Okay, I can tell you some other method as well. Method isn't just how to visualize that. See, this is s orbital and this is the p orbital. Okay, so one orbital of s and one orbital of the p are there for the hybridization process. See, that's why we say this is what? Sp. That's why we say this is Sp. And remember, hybridization is always been calculated for the central atom. In a molecule, you will calculate always for the central atom. Okay. Now, see, you have two orbitals, s and p. Okay. My question is, before the question, just look at this. This is your s orbital. This is your p orbitals. See, we have learned that if two orbitals are participating over there, then after intermixing, they will form the two hybridized orbitals. So we will get 2 such orbitals. Okay. Now, if I ask you in the space, at what angle should I place these 2 orbitals where they feel the minimum repulsion, or they can have the maximum bond angle? How can I place these 2 orbitals in the space where the angle between them is maximum? At what angle they should be present? Are you getting my question, guys? Okay, my question was, see, yeah, absolutely right, Satna. See, you have these orbitals. How can you place these or hybrid orbital in the space so that the repulsion between them is minimum, or we can say that at what angle you can place them so that the bond angle between them is maximum? Okay, let's say suppose these are not the hybrid orbitals. Consider them, this is a line and this is also a line. Okay, this is the line. What maximum bond angle can between these 2 lines have? Maximum bond angle between these 2 lines. Absolutely right, Itanago. Okay, very good, Shillong. Kohiva, I was just saying that these are the 2 lines. Okay, I have just replaced the hybrid orbital with the help of these 2 lines, and now I'm asking where, or we can say how I can place these 2 lines so that the bond angle is maximum between them, or at what angle they are placed so that the angle between them is maximum, or what can be the maximum angle between these 2 lines? Maximum angle between these 2 lines. Actually, if you see, this is already a maximum bond angle, which is 180 degree. Other than that, if you place them at any angle, that angle would be what? Less than 180 degrees. Okay. So very good, guys. You have absolutely right. You have given absolutely right answer. Excited part, yeah, sure, but just let me finish this first. After that, I'll repeat for everyone. Okay, so please just focus on this one. So guys, now let's check out the arrangement of these orbitals. See, these are the hybrid orbitals of the beryllium. Okay, now remember, this is the positive lobe and this is your negative lobe. Remember, other than the hybrid orbitals, okay, it's okay, Kohima, I'll repeat that. Guys, remember that other than these hybrid orbitals, we will always use the normal orbitals. Like S has a spherical shape, so I'll use a sphere. P orbital has a dumbbell shape, that's why I'll use a dumbbell over there. D has a double dumbbell, that's why I'll use a double dumbbell over there. Okay, means the lobes were equivalent over there, but here the lobes are not equivalent. Now my question is, in the BeCl2, I'm talking about the chlorine. Can you please tell me where chlorine belongs to which block? Chlorine belongs to which block? I hope so you have heard about SPDF blocks. So in which block chlorine is present? Yes, P block. Very good. So actually, the last electron of the chlorine enters through the P subshell. That's why I am going to use, for the overlapping purpose, P orbitals of the chlorine. Okay. So what can we do? I'll draw the p orbital. This is positive, negative, positive, negative. See, this is chlorine, this is chlorine, this is beryllium, and this is your bond. This is BeCl2 and the bond angle is 180 degree. First of all, tell me, are you clear that how BeCl2 is formed and why we are saying it is a sp hybridized molecule? Good. Okay, so let me repeat it for the Kohima as they have got shut down. Guys, you can please start copying that. See, this is a ground state. Okay, in the ground state, every orbital means this is the case where every orbital is containing the 2 electrons, means the paired electrons. Okay, so whenever we need to write the excited state, just remember that those orbitals which are having the paired electrons, just make them unpaired. How you can do that? You can just simply shift that electron to the next available vacant orbital. Remember, next available vacant orbital. Look at this, 2s and 2p. So here you can see in the ground state 2p is totally vacant. So that's why I have used the 2p orbital and I have shifted the electron from 2s to the 2p. Okay, and once everyone has become the unpaired, that's why that will become, this one will become what? Excited state. Okay. First of all, excited doesn't mean that all electrons should be, all the electrons should be the unpaired, but yes, it means that the final state where the orbitals can participate in the bond formation. Okay. And here, luckily, we have got a chance where we can make the paired electrons unpaired. Okay. Got it, Kohima? Have you got that? Okay. Just copy and then move on to the next page. Copy this one as well. Copy and then confirm. Okay, Itanagar, Shillong, Satna, Kohima. Dear, have you copied that? Okay, let's move on. Let's talk about BCl3. Let's write the sp2 hybridization. Example is BCl3. Okay. Again, just look at the screen. Boron atomic number 5, 1s2, 2s2, 2p1. This is the ground state. Okay. Now you can draw them like this. This is the excited state. Oh, sorry, not excited state. I'm just drawing the ground state right now. This is the ground state. Okay. First of all, tell me which are the outermost orbitals? Valence orbitals. Tell me the name of the valence orbitals in the given example. Very good, Kohima. Nice, Satna. Fantastic, Shillong. Yes, absolutely right. 2s and 2p are the outermost orbitals. Okay. Now, to make them excited state, what I have to do, I'll simply place the paired electron to the vacant orbital and make them unpaired. Okay. Now, check out only those orbitals which are unpaired. Now, here you can see that this is S, this is P, and this is also what? P. That's why this is known as what? sp2. This is known as sp2. Because one orbital of the S and two orbitals of the P are participating in the given example. That's why this is known as the sp2. You can check out like this. Once they get intermixed with each other, as you can see, there are three orbitals. That's why you'll get the three hybrid orbitals. Okay, such type of three hybrid orbitals. Okay. Now, if I place them these three hybrid orbitals in the space, so at an angle of 120 degrees, they will suffer the minimum repulsion. So look at this, how to draw that. See. Okay, these are the arrangement of the hybrid orbitals for the boron. Now, other element is what? Chlorine. So I'll use its outermost orbital, which is the P. So this is representation of the chlorine. Okay, and check out minus, plus, plus, minus, 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 plus, 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 minus, plus, minus. Okay, see, beryllium, sorry, not beryllium, boron, chlorine, 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 angle is 120 degrees. Copy, please. Any doubt about it? You have to start with this one. Copy. Any doubt, guys? If yes, you can please ask me. If not, then you can copy it down. Just copy and then confirm. Okay. Why 120 degree here? Okay. First of all, copy that, then I'll tell you. Copy and then confirm. Or fill as in electron. Means you need not to write that, but yes, you can. In case of SP or 3D, I'll tell you that there you will mention that. Okay, because I won't draw these such diagrams over there. Copied? Okay. Now, this is just a question. I hope so everybody is clear with this one. But just because one has got some doubt. See, these are the 3 sticks actually. 3 sticks. You have to join these 3 sticks. Okay. At this point, what can be the maximum angle between each and every stick? You have to tie these sticks here like this. Means you can place them at any angle. My question is, what can be the maximum angle between these sticks? Yes. Absolutely right, Kohima. Satna, are you getting my question? If not, you can please tell me. I'll change the question. I've just asked that what can be the possible angle between these. I asked you the maximum angle. Oh no, Shillong. 360 degrees only possible around a point actually, in a circle. This is also a circle, you can say. Okay, fine. Let me check out. Yes, absolutely right, Shillong. If I put it as a 90, this one is 90, this one is 90. So the total sum is actually 270 degrees, na? But I know the total between the between the 3 sides, the angle between 3 sides, the maximum sum can be 360s. Are you getting, Satna? Maximum can be what? 360. So I don't think that maximum has reached over there. Look at this. Why are you placing them perpendicular to each other? Just place them at an angle of 120 degrees, na? See? You will get your answer. Got it now? Very good. Let's move on. Because next question you have to answer. See, in the sp hybridization, the sum was 360, 180 above, 180 below. Second one, the bond angle was 120. There were 3 bond angles. Okay. Now next part, sp3. Okay. Okay, consider them as a 4 sticks. One orbital s. Obviously, there are total 4 orbitals. They will form the 4 hybrid orbitals. So, what will be the possible bond angle between the 4 hybrid orbitals? What will the maximum bond angle between them? Tell me. No, Kohima. I said maximum. Okay. If I say 109 degrees, 27 minutes. If I say 109 degree 27 minutes, think about one thing. Is that possible that the four lines can be mutually perpendicular to each other? I think so. There are three axes which are mutually perpendicular to each other, and which can have the maximum bond angle of the mutually perpendicular means they can have the bond angle of the, or the angle between them is 90 degrees. I said the four. So in case of four, how can you place them mutually perpendicular to each other? Think about it. How can you place the four sticks which are joined at a particular point? Look at this. Look at this. Four sticks tie on this particular point. How is it possible that the angle between them would be 90 degrees? And one thing, 90 degrees is not the restricted part. I have asked you the maximum angle, and I'm saying, in spite of 90 degrees, think about it. 109 degree 27 minutes. So which one is maximum, 90 degrees or the 109 degree 27 minutes? Confused? Tell me quickly. Confused? You leave a point in the statement. That's why you're getting the wrong answer. Confused? Okay. Now wait. If you are got confused, now wait for some time. Or let me finish it first. Then you will get that. Okay, carbon 1s2, 2s2, 2p2. This is a ground state. This time, guys, I am directly drawing the excited state. See, this is the ground state, but I have to draw the excited state. So to draw the excited state, I'll make the paired electrons as an unpaired electron. So one electron from 2s will be shifted to the 2p. Now you can check out very clearly. Here, the four orbitals are there, which are actually half filled. Okay, they all will participate in the bond formation. So S, Px, Py, and Pz. That's why this is known as what? sp3. Okay. Look at this. S, four orbitals, and we will get such four hybrid orbitals. Okay. Now I am placing these four hybrid orbitals like this. One second, guys. 1 second. Let me draw it a little bit clear. This is the arrangement of the four orbitals. Now, a CH4 mean next surrounding element is what? Hydrogen. So the outermost orbital would be what? S. So that's why this one will have got the spherical shape. And you can check out. Carbon, hydrogen, 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 hydrogen. And the bond angle is 109 degree 27 minutes. Copy, please. Oh, copy. Copy. Copy this one. Done. Okay, now tell me how many of you got haven't got that the bond angle is 109 degree 27 minutes. Let's understand this if you have doubt. 90 wouldn't be the answer for sure. If you have got clear that, okay, let's continue. Let's start with this one. First of all, guys, first of all, remove one thing from your mind, that the sum here will be the 360. In the first two cases, it was possible that the sum was 360, but here it is not possible. Okay. Now tell me one thing. Tell me one thing. If I put the bond angle 90 degree, is it possible that the all four bonds will be at the 90 degrees? I'm saying this one. Everyone please just confirm it. These are the four sticks. Four sticks. Is it possible that all the bonds can be 90 degrees? Yes, very good. It is not possible that all the bonds would be the 90 degrees. Okay. So first of all, remove that concept that here the bond angle would be the 90 degrees. Okay. Now, second part. The point was saying that what should be the maximum possible bond angle between these four lines which are connected to each other. Guys, just look at this. Look at this arrangement. Look at this arrangement. Okay. Now, this is a kind of tetrahedral. Have you ever seen the tetrahedral, guys? Have you ever seen the tetrahedral? Just confirm. Have you seen the tetrahedral? What is the bond angle in the tetrahedral? What is this? Theta in the tetrahedral case? Can anyone please tell me? Tetrahedron is actually a 3D geometry over there, where the center, I'm talking about this one. Okay. Every angle is 109 degrees. Now, if I change any of the angle from 109 degrees, now this is not possible if I talk about the regular tetrahedral. Regular means where bond angles are actually exactly perfect over there. Okay. So, this is actually the tetrahedral geometry where in the space you can put the four lines exactly at the 109 degrees 27 minutes. Okay, this is the maximum possibility over there. Okay, don't confuse that the four bonds are there actually, and if four bonds are over there, then if I multiply this one with the 4, I'm sure you won't get your answer. That's which you were expecting initially. Okay, so don't confuse with that. This is the mensuration section, not the geometry section. In the geometry, we have got the circle, we got the triangles. Okay, in the 3D, actually that was a 2D concept, but this is what a 3D concept over there. Okay, so in the 3D concept, this is the maximum possible arrangement over there. Okay, so first of all, differentiate between the two terms, that this tetrahedral is actually what 3D arrangement over there, where you can get the maximum bond angle of the 109 degrees. Okay, now clear? Or still some confusion? Ultimately, I am trying to say over there that the 4 bonds are there, 4 sticks are there ultimately, and these 4 sticks, when I tie to a particular point, they will be forming a tetrahedral, and the every bond over there will be 109 degrees 27 minutes. Okay, this is the actually experimental determined values over there. Okay, so can you move on? Okay, now let's check out the next example. Talk about the ammonia. 7, 1s2, 2s2, 2p3. Now guys, the problem here is, or 2p is the orbital which was vacant initially for the atoms or elements which were just before the nitrogen. But in the nitrogen, the 2p orbitals even containing the unpaired electrons. Okay, but the problem is here, there is no extra vacant orbital over there. Okay, no extra orbital vacant over there. Okay, but yes, actually these orbitals would participate for the hybridization purpose. That's why sp3, this is s, px, py, pz. This one is also known as what? sp3. Okay, now one thing, first of all, I'll make the same arrangement for the sp3. Okay, first of all, tell me guys, in the given example, how many orbitals you can see over there which are unpaired? How many orbitals are there which are unpaired, which are containing the unpaired electron? Exactly, 3 are there. That's why only 3 bonds will be formed over there. See, this is the concept actually. Only those atomic orbitals which are forming the hybrid orbitals having the unpaired electrons can form bonds only. And those who are having the fully filled orbitals will become the lone pairs. Okay, so it is your choice. You can pick any of the 3. I have chosen these 3. Okay, and this one will become the lone pair. Okay, this is the formation of the ammonia. And you can draw this one like this as well. This is nitrogen. One second. Okay, H, H, and H, and this is your lone pair. Okay, clear with the ammonia molecule? Clear guys? Copy. Okay, copy please. Shillong, Itanagar, Kohima, guys, are you clear with this one? If not, you can please ask me. Okay, copy this one as well. this one. Copied? Guys, I'm giving you some time. H2O. Explain H2O. Hybridization in H2O by using the same method. You can start. And just after just after finishing them, just you can revert to me that you have done with that. Okay, Satna. Shillong, Kohima, Itanagar. Guys, have you done that? Okay, good. So let's begin, guys. Check out the oxygen, which is 8, 1s2, 2s2, 2p, 4. So if you check out the arrangement, it will look like this. Two electrons, 1 and 1. So obviously in the hybridization process, 1s and 3p would participate, but yes, only those orbitals which are unpaired, which contains the unpaired electron, will form the bonds. So I can see that here only 2 such orbitals are available. Okay, that's why this one will form the 4 bonds. Sorry, 2 bonds only. Okay, so I can simply say this is the oxygen at the center. Okay. This hydrogen, this is hydrogen, 2 bonds have been formed and rest 2 are lone pairs. Have you done the same, guys? Those who have attempted that, I have used little bit of shorten method. I have written a few steps over there. I hope so you have understand that. Understood, guys? Kohima, Satna, Shillong, Itanagar. Okay, good. Those who haven't done that, just please copy that, and then we'll next move on to the next molecule. Guys, please mark your attendance. Everyone, please mark your attendance. Shillong, Kohima, Satna, Itanagar. Okay. Okay, Satna, Itanagar. Guys, look at these examples, CH3, CH3. First of all, I'll tell you the expanded structure of this one, and after that we'll draw its hybridization. What about you, Kohima? Mark your attendance. And guys, now please look at the screen very carefully. If you want, you will just miss the step, and this is very much important for the boards, or we can say the school examinations, and for the entrance examinations, they mostly ask you the hybridization, how we can calculate the hybridization. Okay, I'll tell you the both the methods. I'll discuss that method later on. Okay, once I have already discussed that, but now just I have to brief that. Okay, just look at this. So if I expand the CH3, it will actually look like this. Okay, see, sigma, 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 sigma. This is sp3 hybridization, and this one is what? sp3 hybridization. And we know that how, in case of sp3 hybridization, we have to place the atomic orbitals. Okay, so I'll check out one by one the 2 carbons over there. Okay, see, on the left hand side of the carbon, all 4 bonds are present. Okay, that's why I need to make the 4 hybrid orbitals. As well as on the right hand side, I need to make the 4 sigma bonds. That's why I'll draw the 4 hybrid orbitals. Okay, first of all, I'm drawing the carbon on the left hand side. Okay, and first of all, I'm drawing the sigma bond between the two carbons by using the 1 hybrid orbital. I'm drawing the sigma bond between the 2 carbons. Check out this one. Look at this. See, carbon, carbon. Overlapping region, I need not to overlap this one. I need not to shade that. 1 second. I'll redraw it. I won't shade it again. Okay. So this is the sigma bond between the 2 carbons. Okay. So I think so I have completed this part. This bond is formed. Okay. Now I am going to draw the 3 sigma bonds on the left hand side of the carbon. Okay. Look at this. Check out this one. Guys, for some time, just hide the carbon on the right hand side, the hybrid orbital of the carbon on the right hand side, and just look at the hybrid orbitals present on the left hand side. One second, let me make it much more appropriate. One second. So it would be easy to visualize. Yes, now. Hide the hybrid orbital on the right hand side and check out the carbon on the left hand side. Is it look like a tetrahedral that we have just draw in case of the CH4? Is it look like that? Okay, yes, actually this is that one. Same you have to draw on the right hand side. Same we have to draw on the right hand side. Okay, just place the hydrogens here. 1, 2, 3. 1, 2, 3. So guys, this is your CH3 molecule. Look at this. Okay, got it? Cleared everyone? Copy please. First of all, copy this one. Guys, are you clear with that? If not, you can please ask me. Okay, now you may copy this one. Please copy this one, guys. Very much important for the school examinations. Copy and then please confirm. Okay. Shillong, Kohima and Itanagar, dear, have you copied that? Okay, nice. Now check out the next one, guys. That's quite much more important. Okay, and it's very important to visualize that. Okay, the example is ethene, CH2, and the expanded structure for this one is this one. Sigma, 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 pi, sigma, sigma. Guys, check out this carbon. This carbon. You can see here, this carbon is forming the 3 sigma bonds and the 1 pi bond. And if you check out the next carbon, the same is observed over there. There is a 3 sigma bond and 1 pi bond. First of all, clear one thing that hybridized orbitals can form only sigma bonds. They can never form the pi bonds. Pi bond will always be formed by the simple orbitals by the sideways overlapping. Okay. So, for a while, to draw its structure, forget about the pi bond. We know that in case of the carbon, I can have the 4 orbitals. Okay. Out of 4, 3 are forming the sigma bonds. It means that there are 3 hybrid orbitals. Fourth orbital which is left over there, fourth orbital will be parallel to the internuclear axis and it will be participating for the pi bond. Okay. I hope so you are getting this. So I'm drawing this. Just look at the screen. First of all, I'm drawing for this carbon. Okay, look at this. I'm using the hybridized orbitals over there. Okay. Look at this. One second, guys. This is sp2, and this is also sp2. And I hope so that you know how, in case of sp2, we can place the atomic orbitals. So I'm doing the same. See? This is the left hand side of the carbon, sp2. One second. What's happening? Yeah, a little bit. Okay. Just manage with that, guys. I can make it a little bit better. Yeah. So I hope so you are clear with this one. Okay, just put the hydrogens. I hope so you are clear. Look at this. 2 sigma bonds with the hydrogen on the left hand side and 1 sigma bond with the carbon. Okay. Now, up to this one is clear to everyone, guys? Just confirm once. Are you clear with this one? Up to this? Okay. Now we are left with the 4th orbital. And this 4th orbital won't be the hybridized orbital, that will be the normal orbital. Okay. So I'm going to draw the normal orbital over there. This is your 4th orbital, which is actually perpendicular to the internuclear axis, and this one will overlap to give you the pi bond. So this is forming the pi bond. This is sigma, 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 and sigma. This is the hybridization diagram for the what? Ethene. Copy. First of all, copy this one, guys. Copy and then confirm. If you have any doubt or query, you can please ask me. Even you can ask in the group as well, or still right now, if you have any doubt, you can please ask me. If not, then just copy it and confirm it to me. Okay. One second, guys. Shillong, please confirm after copying that. Take your time to copy that, but intimate me after copying that. Okay, very good. Have you done this one as well? If anyone of you haven't copied that, please you can copy that. I'll tell you that how this sp2 is coming over there. And guys, please confirm everyone is clear with this one. I hope so. Nobody is having any doubt. If yes, you can please ask me. Okay. Okay, very good. Shillong, Satna, Itanagar, and Kohima, guys. Okay. So guys, that's all for today's session. We have left with one more hybridization over there, which is SPSP. Okay. Which is SPSP over there. Okay. CS3, CS3, ethine we have to discuss, and after that I'll tell you that how you can determine the hybridization in any molecule over there. Okay. So guys, I'll discuss that part in the next class. Okay. Please make sure you will revise it thoroughly again. Okay. And if you have that doubt or query, you can please send that one to the WhatsApp group as well. Okay. So guys, till then, take care. Bye-bye. Thank you so much. Please stay healthy. Take care of yourself. See you next time. Bye-bye.